Hello and welcome to the Unit 1 podcast on Section 4.3. Here we're going to be talking about what makes atoms different from others.
I'm Mr. Lin.
And I'm Mr. Sakaguchi, and away we go.
And we're still here.
Any time now. There we go.
There we go.
Atomic number is one of the features that distinguishes elements from other ones. And basically, atomic number is the number of protons for an atom.
Realize that for neutral parts of the for neutral atoms, the atomic number is going to be equal to the number of protons and the number of electrons. That way, their charges cancel out, so that way it's neutral. Things to be aware of when you're reading these tiles is that the atomic number and the atomic mass get moved around a lot depending upon who's printing out the periodic table. So what you want to keep aware of is that the atomic mass is going to be the larger number and the atomic number is going to be the smaller one.
Yeah, so the atomic number is going to be the whole number. Atomic mass will have the decimals. There are also things known as isotopes, and these are basically atoms that have the same number of protons but different numbers of neutrons.
So isotopes, first up also is to recognize that this modifies Dalton's atomic theory, because he once stated that all atoms of the same element are identical. With the feature of isotopes, this is an exception to that rule.
In nature, most elements are not found, if they are found pure, they're not just one isotope. Usually there's a mixture of isotopes. We express isotopes in different ways. One way is to do this symbolically, where you'll see a number in the upper left and a number in the lower left. The lower left number represents the atomic number, or the number of protons. This number here represents the number of protons plus neutrons, which is also known as the mass number.
And this will help you identify between the different types of isotopes.
Individual atoms have, have their own masses. We use atomic mass units, which I mentioned in a previous podcast, as a way to measure mass. This is also known as AMUs. It's a relative measure based upon carbon-12, so it's simply 1/12 the mass of a carbon-12 atom.
The reason this was chosen is because carbon-12 is the most easily obtainable and easily found pure element.
What we find is that one AMU is basically approximately equal to the mass of a proton, which is approximately also equal to the mass of a neutron.
They're off by just a little bit, but we're talking about decimals, and it's really tiny, so we just stick with the ones.
So if this is all true, why aren't atomic masses actually whole numbers? And there's a reason why that is.
And you'll see that on your periodic table, because the different elements will have decimals instead of just whole integers.
Which leads us to atomic mass. Atomic mass is basically a weighted average of the isotopes of that element.
A weighted average is kind of like your GPA, where your grade value gets averaged in together with all the other grades, and that gives you your GPA. Same thing with the atomic mass, where you have the average, or the amount of different types of isotopes put in together percentage-wise, and you add it all up, and that gives us your atomic mass.
Yeah, so this is when the probabilities of something happening are not equal to each other. So with respect to our isotopes, there are different isotopes.
And some occur more often than others.
Yeah. You may have to do atomic mass calculations in your class, and basically you can do it in a few simple steps. The first step basically is to take percent abundances that are given to you and turn them into decimals by moving the decimal places two places to the left. So for instance, 94.3% would become the decimal 0.943.
The next step would be to multiply the mass of that isotope by that decimal that you, or percent decimal that you just solved for in step 1.
Now sometimes that mass may be just the mass number itself, depending upon the problem, and other times they may give you a specific mass that's a little bit more accurate a measure for a particular isotope.
But essentially what you do is you multiply the percentage by the mass for the isotope, and then you just do that for all of the isotopes.
So for instance, if there are 3 isotopes, you would do 3 multiplications.
And add them all up.
And then you label your answer in AMU, and then hopefully you get it right. Here's a sample mass problem. So here we have 2 different isotopes of chlorine. So here's an example. So one thing for notation-wise, sometimes you'll see the name of the element, a dash, and then a number. This number represents the mass number. This allows us to this is another way to represent isotopes. So this number you see after the dash is the mass number of protons plus neutrons. You'll also notice that you're given a more specific mass in AMUs, which is what we're going to use for our calculation, and then corresponding percent abundances.
So just like with the steps that we talked about in the previous slide, you can see that you have your mass and then the percentage, and we move the decimal over a couple of spaces to the left, multiply them together. That gets you your first AMU value, and then you repeat the process for the other isotope, and then they'll take those answers, those values, add them together, and that winds up being your atomic mass.
And that is it for now.